Welcome, my dear students. So in the previous lectures we have discussed about bounded linear operators. So in this lecture we are moving on to a new class of functions or operators and its properties. So definition. Two operators T1, T2 are said to be equal which is written as T1 equal to T2 if they have the same domain that is d of T1 should be equal to d of T2 and T1x is equal to T2x for all x element of d of T1 which is equal to d of T2. So two operators T1 and T2 are said to be equal if their domain is equal and the values at the corresponding points are equal. If this condition satisfied, these two conditions satisfied, then we can say that the two operators are said to be equal. Now another definition, I think you might have heard about restriction and extension of a function. Similarly, we can define restriction and extension of operators as well. So the restriction of an operator T from dt to y to a subset B subset of d of t is denoted by t restricted to B and is the operator defined by t restricted to B from B to y such that t restricted to B x is equal to t of x for all x element of B. So if this condition holds, then we call this operator T as the restriction of the given operator T. And similarly, we can define an extension of the operator. So restriction means we are restricting the operator onto a subset of the domain. Extension means we are extending the operator onto a superset. So definition, an extension t extension of t to a set M superset of d of t is an operator t tilde from M to y such that t tilde restricted to d of t should be equal to t. That is t tilde of x should be equal to d of x for all x element of d of t. Okay, so from this perspective itself we can define the extension. Here the operator t, which is defined on the set d of t to y, is defined on a subset b of d of t. Such an operator is called the restriction. Then t is called an extension of this operator, t restricted to b. What we are doing is we are defining an operator, then we are considering a subset of the domain of the operator, and we are restricting that operator onto the subset. That operator is called, the new operator is called, which is defined on the subset, is called the restriction. And then the original operator can be termed as the extension of the new operator. Similarly, an extension of t which is defined on some d of t is actually an operator which is defined on the superset of the domain. Instead of d of t, we are actually considering it as a superset of t of t, and that operator is denoted as t tilde, and it is defined as t tilde. It should satisfy t tilde restricted to d of t should be equal to t, or t tilde's restriction should be equal to t. If t tilde is called an extension of t, then t should be called the restriction of t tilde. That's the thing. So I think I can try to represent a pictorial representation as well. So this is actually d of t, okay, and this is actually y. And t is a function from, so first case t is a function from d of t to y. Now consider a subset. This subset is called b. Now if we are defining this function not from the whole d of t, from only b to y, only b to its images t of b, okay, we should be a subset of y as well, then this is called t restricted to b. So t is a function which is defined on the whole set d of t. Consider any subset b of d of t and define this function which is restricted onto b. Such a function is called t restricted to b. Please remember that this restriction is actually the function t itself. We are only doing that, we are only defining this function on a proper subset of d of t. That's what we are doing. We are not changing the function definition. And then this is the restriction. If this is the restriction, then t can be called as the extension of t restricted to b. Or in other words, if you are defining a function from some d of t onto y, and if you take a superset of d of t, this is actually a superset which is called M. Now the original function was from d of t to y. If you can define a new function which is from M to some superset of y, maybe onto y itself, this function is called the extension of t. Okay, so the extension, there is a common part which is actually d of t. In the common part, t and t tilde should be same. So t is actually the restriction of t tilde. Then only we can call t tilde as an extension. This is actually the meaning. So actually we are defining or we are extending a function onto a bigger set, then such a function is called the extension. If you are restricting the function on a proper subset, then the function is called the restriction. That's it. Now, why we want to do this, why we want to study this actual extension and actual restriction? The main motivation comes from the fact that every space need not be complete actually. So in order to make the space to be complete, we might have to add some other elements. So if you are given a space, it may not be complete. So actually if you add some elements, or if we take the closure, or if you add some element to onto x, we get a bigger set which is denoted as x tilde or x bar, which may be complete. Okay, now if you are defining an operator t which is maybe continuous on x, which may be bounded on x, now the natural question is, you are only adding some other elements onto x to define x bar. Now if at all, can you extend this function which was defined on x to its a bigger set x bar without actually compromising the properties? T has the property continuity as well as boundedness. Let's assume. Now, if you are defining T onto x bar, can you keep the continuity as well as the boundedness? Or T also possesses continuity and boundedness when it is defined on a superset of x, or if T at all extending onto a superset, can its linearity or boundedness or continuity can also be maintained, or does that varies? Does the linearity varies? Does the continuity varies? Does the boundedness varies? That's the basic idea behind the whole thing. If a function which is defined on a superset has a linearity, then its restriction should also has linearity. Okay, it also possesses the boundedness, it also possesses the continuity. Okay, now the natural question is, can you possess, can you extend this function onto a bigger set without actually compromising any of these properties, the properties linearity, continuity, boundedness, etc., etc. That's what we have to observe. Okay, that's why we are actually defining extension, restriction, etc. So our objective is, we are trying to extend an operator with a certain properties such as linearity, continuity, boundedness, in such a way that it does not compromise the properties. You are actually extending that function without actually losing any of its properties. If such a possibility exists, which may be useful for further studies. That's why we are actually studying these things. Okay, so that's what we are going to do in the next theorem. So the theorem is, theorem 2.7.11, which is bounded linear extension. Bounded linear extension. We are actually trying to extend a linear function onto its superset without actually losing any of its properties. So let t from dt to y be a bounded linear operator where d of t lies in a normed space X and Y is a Banach space. Please remember this argument. Y should be a Banach space. Y should be a complete normed space. Then T has an extension. Then T has an extension T tilde from d of t closure, which is actually a superset of d of t, onto y, where t tilde is a bounded linear operator, say bounded linear operator of norm t tilde should be equal to norm t. This is the theorem. So it states that if you are given with an operator t from d of t to y, where d of t is a subset of a normed space X and Y is actually a complete normed space, or it's a Banach space. This argument is very important. You should not be considering Y as a normed space. It should be a complete normed space where T is a bounded linear operator. Then T has an extension or T can be extended onto its closure T tilde from dt closure onto y, and the extension is also a bounded linear operator, and also both t tilde and t has the same norm. Or if you are given with a bounded linear operator from a normed space onto a Banach space, it can be extended onto its closure such that the extension is also bounded linear operator, and also it has the same norm. That's the theorem. So now we have to prove this. So let's move on to the proof part. So proof. So you are given with a linear operator t from dt to y, which is actually a bounded linear operator. Now we have to define an extension of t from to dt bar onto y. So consider an x element of dt bar or dt closure. Then by theorem 1.4.6a, every element in the closure can be defined as a limit of a sequence which is defined on the space. So there exists a sequence xn element of dt such that xn converges to x. This theorem states. So you should be noting this theorem. Now t is linear and bounded. So norm of txn minus txm should be equal to, since t is linear, it should be equal to t of xn minus xm. Now t is bounded, t of x should be less than or equal to some constant norm t into this thing. So norm t of x should be less than or equal to norm t into norm x, since t is bounded. So this should be less than or equal to norm t into norm of xn minus xm, since t is actually bounded. So given that xn is given that xn is convergent, which implies xn is Cauchy. So norm of xn minus xm should be less than or equal to epsilon by norm t for all m comma n greater than or equal to capital N. So if you substitute that onto this, we get norm of txn minus txm should be less than or equal to norm t into epsilon by norm t for all n comma m greater than or equal to capital N. Now if we cancel norm t, we get norm of txn minus txm is actually less than epsilon. So what we get is norm of txn minus txm is actually less than epsilon. We only need less than. Okay, so for all n comma m greater than or equal to capital N. Here there is no less than or equal to, only less than. So which implies that t of xn is actually Cauchy. Also, t of xn is a sequence in y, and y is actually complete. Y is complete. That's why we need that y should be a Banach space. This is why we need that argument. So t of xn is Cauchy implies t of xn is convergent. T of xn is convergent. This convergent, Cauchy implies convergent argument only valid whenever y is complete. So t of xn should converge. Let t of xn converges to y. Okay. Then this y can be termed as the image of x with respect to t tilde. So now define t tilde from dt closure onto y as t tilde of x is equal to y, because for every x element of d of t closure we found a sequence xn element of d of t such that t of xn converges to y. This y is called the image of t tilde with respect to x. That's why we define. So t tilde is defined. Now we have to establish that t tilde is independent of the choice of this xn. Corresponding to x, we have defined a particular choice of xn. For that, we have to choose two sequences xn and yn such that both of them converges to x. Then its images t of xn and t of yn should also be converging to the same point. So let xn converging to x and yn converging to x, where x is an element of d of t closure. Now we define a new sequence Zn, which is defined as x1 y1 x2 y2 x3 y3 etc. We are alternating inserting the terms of xn and yn. Since this has two parts, this is Zn is actually xn if n is odd and yn if n is even. Since xn converges to x and yn converges to x, both of these subsequence converges to x. So we can clearly understand that the sequence Zn converging to x. Now, since t is a linear operator, linear, by theorem 2.7.10a, Zn converges to x implies t is linear implies t of Zn converges to t of x. Okay, t of zn means actually zn has two parts, so t of zn should be converging to t of x. So t of zn has two parts. One is t of xn when n is actually odd, and t of yn when n is even. So t of zn converges to t of x. It has two subsequences, and t of zn converges means every subsequence of t of zn also converges, and subsequent should be converging to the same limit as well. So t of xn and t of yn should converge to the same limit. Okay, that is, we have taken two sequence xn and yn, both of them converging to x, then its limit t of xn and t of yn should converge into the same limit t of x. This is can be called y, which is defined as t tilde of x. Okay, where x is an element of d of t closure. So corresponding to two different sequences also, our limit is actually same. So our definition is independent of the choice of the sequences. So that part is established. Now we have to prove that our t tilde is linear. So t tilde is uniquely defined. Now we have to prove that t tilde is linear. So for that we have to prove that t tilde of x plus y should be equal to t tilde of x plus t tilde of y. So it is trivial. Corresponding to x, we must have a sequence xn which converging to x, and corresponding to y, we must have a sequence yn converging to y. Okay, so t tilde of x plus y, so xn converges to x and yn converges to y means xn plus yn is a sequence which converges to x plus y. So corresponding to x plus y, we must have a sequence xn plus yn which converges to x plus y. So t tilde of x plus y is actually limit n tends to infinity t of actually xn plus yn. Okay, that's how we have defined it. Okay, if y is actually the limit of t of xn, the limit n tends to infinity t of xn. Since t is linear, this can be written as limit n tends to infinity t of xn plus t of yn. Now splitting the limits, so this is equal to limit n tends to infinity t of xn plus limit n tends to infinity t of yn. So t of xn is actually t of xn converges to t of xn converges to t tilde of x, because xn converges to x, limit of t of xn should converges to t tilde of x. Okay, so this should be equal to t tilde of x plus t tilde of t of yn converges to t tilde of y. This is what. So the first part is trivial. Now the second part is, so t tilde of alpha x. Corresponding to alpha x, we have a sequence alpha xn which converges to alpha x. So t tilde of alpha x should be equal to limit n tends to infinity t of alpha xn by the linearity property. So which should be equal to limit n tends to infinity alpha t of xn. So it should be equal to alpha into limit n tends to infinity t of xn. Since t is a linear function and also xn converges to x means t limit tends to infinity t of xn is actually t tilde of x, so which is equal to alpha t tilde of x. So the both part is established, so which means that t tilde is actually a linear operator. Now we have to prove that our T tilde is actually an extension. So T tilde is an extension. So okay, so in order to prove this, we have to prove that norm of T tilde should be equal to T, okay, for all and on D of T. That's what we have to prove. And for every x element of D of T, we have a sequence which is defined as xn is equal to xxxx etc., which is actually converges to x, which is the constant sequence. Then T of xn is actually T of x etc., which is a constant sequence which converges to T of x as well. So for every x element of D of T, limit n tends to infinity, T of xn, which is that sequence is defined as this is actually T tilde of x, okay. So this should be equal to T of x, because limit n tends to infinity, T of xn is actually T tilde T of x, okay. So T of x and T tilde of x are actually same. This is using the definition of T tilde, and the second part is obtained by taking the limit of T of x. And so for every x element of D of T, T tilde of x should be equal to T of x. So T tilde is defined for every x element of D of T, and both of them are same with regards to this on the D of T. And we have already defined that T tilde is defined on for every element of D of T closure as well. So T tilde is defined on a superset of T D of T as well. So which means that T tilde is actually an extension. Using this, we have established that T tilde is an extension. Okay. Now the only thing which remains to prove is the fact that T tilde should be bounded. We have proved that T tilde is a linear operator, T tilde is an extension. Now we have to prove that T tilde is actually bounded. So consider that for every x, we have a sequence xn belongs to D of T such that T of xn converges to xn converges to that, and we have proceeded like this. And also corresponding to every sequence xn, we have norm of Txn should be less than or equal to norm T into norm xn. This is true for all xn. For any sequence xn belongs to D of T, this is true because T is assumed to be linear. Now taking n tends to infinity, as n tends to infinity, T of xn tends to y, which is termed as T tilde of x. So, and also x tends to norm x defines a continuous map. We have already defined a continuous map. So which means that T of xn converges to y implies norm T of xn converges to norm y. That's this means, okay. So norm of T of xn converges to this y, which should be equal to T tilde of x. So as n tends to infinity, norm of T of xn should be equal to norm y, which should be equal to norm of T tilde of x. So as n tends to infinity, on this part we can substitute it as this part as norm of T tilde of x, left hand side. This is independent of n, so this should be equal to norm T into, and also xn converges to x means norm xn converges to norm x, so this should be equal to norm x, okay. Xn converges to x means norm xn converges to norm x. So from this we can understand that norm of T tilde of x by norm x is actually less than or equal to norm T. or norm t is actually an upper bound of this quantity, norm of t tilde of x by norm x. Okay, now this norm t tilde should be equal to supremum x element of d of t bar x not equal to 0, norm of t tilde of x by norm x. And supremum is always less than or equal to upper bound. Supremum is the least upper bound. So this should be less than or equal to norm t. Okay, so which implies that norm t tilde should be less than or equal to norm t. And from this we can clearly understand, if you take this as C, you can clearly understand that this is actually bounded. So t tilde is actually bounded. So from this we can clearly understand that. From this, norm t tilde should be less than or equal to norm t. Also, it is clear that norm of t is always less than or equal to norm of t tilde, because t is defined on t of t, and we are taking the supremum of norm t of x by norm of x on for every x element of d of t, and t tilde is defined on a superset. Okay, so clearly the supremum which is defined on the superset is always greater than the supremum which is defined on the subset. T tilde has the supremum of this quantity which is defined on the superset. So clearly norm of t should be less than or equal to norm of t tilde. From these two, if equation number 1 and equation number 2, from these two we can clearly understand that norm of t should be equal to norm of t tilde. So all the properties have been satisfied. T tilde is, there exists an extension which is called T tilde, which is actually linear, which is bounded, and has the same norm. Okay, so every linear operator which is defined from d of t to y, where y is a Banach space, has an extension which that extension is also a bounded linear operator. So I hope you understood. Thank you.